Imagine yourself beside a quiet stream. The water flows gently over smooth stones, catching fragments of light. Each ripple carries reflections of the sky above. The sound is soft and constant, a rhythm that has played since the world was young. Tonight, we journey through one of the most remarkable substances in existence, water. It falls from clouds, rises from oceans, and flows through every living thing. It is so familiar that we rarely pause to consider how extraordinary it truly is. There is no test at the end of this journey, no need to remember anything. Simply let these peaceful facts wash over you like gentle rain, carrying you slowly toward rest. Welcome to Sleepy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep while learning something new. Either way, this journey is for you. There is something deeply calming about water. The sound of rain on a roof, the sight of waves rolling toward shore, the feeling of mist on your skin. Throughout human history, people have gathered near water to find peace. Tonight, we will explore why water is so special, not just for our planet, but for the entire universe. Water exists in places we never expected and behaves in ways that still puzzle scientists. So let the weight of the day drift away. Let your thoughts grow soft and slow, and let us begin our peaceful exploration of the most essential substance on Earth. Water covers about 71% of Earth's surface. From space, our planet appears as a brilliant blue sphere. This color comes from the vast oceans that wrap around most of the globe. Water dominates our world in a way that makes Earth unique among the planets we know. The oceans alone contain about 97% of all Earth's water. The remaining 3% exists as freshwater in glaciers, ice caps, groundwater, lakes, rivers, and the atmosphere. If you could gather all the water on Earth into a single sphere, it would be about 860 miles in diameter. That might sound enormous, but compared to the size of our planet, it is surprisingly small. Our water supply is precious and finite. This delicate blue film of water is what makes life possible on Earth. Without it, our planet would be as barren as Mars or as scorched as Venus. Every molecule of water you drink contains atoms older than the sun. The hydrogen atoms in every glass of water you drink are among the oldest things in the universe. They formed in the first moments after the Big Bang, nearly 14 billion years ago. Before there were stars or galaxies, there was hydrogen. The oxygen atoms are younger, but still ancient. They were forged inside massive stars that lived and died billions of years before our solar system formed. When those stars exploded as supernovae, they scattered oxygen and other elements across space. Eventually, hydrogen and oxygen atoms met and bonded together, forming water molecules that drifted through interstellar space. Some of those molecules became part of the cloud of gas and dust that collapsed to form our sun and planets. The water you drink today carries the memory of cosmic events that occurred before Earth existed. In a very real sense, every sip connects you to the beginning of time. Water is the only common substance that exists naturally in all three states on Earth. Walk outside on a winter morning and you might see ice on the ground, liquid water in a stream, and water vapor rising as mist. No other everyday substance appears in solid, liquid, and gas forms under normal Earth conditions. This versatility is crucial for life. Ice forms protective layers on lakes, allowing fish to survive winter. Liquid water fills oceans and flows through our bodies. Water vapor rises into the atmosphere and falls again as rain. This endless cycle has been running for billions of years, and every living thing depends on it continuing. A single water molecule can cycle through the atmosphere in just 9 days. Water molecules are constantly on the move. A molecule that evaporates from the ocean might spend only about 9 days in the atmosphere before falling back to Earth as rain or snow. But that same molecule might then spend thousands of years frozen in a glacier, or it might seep underground and remain in an aquifer for tens of thousands of years. The residence time varies enormously depending on where the water goes. In rivers, water typically stays for only a few weeks before reaching the ocean. In the ocean itself, a water molecule might circulate for about 3,000 years before evaporating again. Over the course of Earth's history, every water molecule has cycled through the atmosphere, oceans, ice, and living things countless times. The water in your body has been part of this cycle since the planet formed. Ice floats on water because it is less dense than liquid water. This seems so ordinary that we rarely think about how strange it is. Almost every other substance becomes denser as it freezes. Solid iron sinks in molten iron. Solid rock sinks in magma. But ice floats. When water freezes, its molecules arrange themselves into a crystalline structure that takes up more space than liquid water. This makes ice about 9% less dense than the water around it. The consequences of this quirk are profound. Lakes freeze from the top down, creating an insulating layer that protects aquatic life below. If ice sank, lakes and oceans would freeze solid from the bottom up, making complex life impossible. This one unusual property of water may be the reason life exists on Earth at all. Water has an unusually high heat capacity. It takes a remarkable amount of energy to heat water. This property, called high heat capacity, means that water can absorb or release large amounts of heat without changing temperature dramatically. This is why coastal cities have milder climates than inland areas. The ocean absorbs heat in summer and releases it in winter, moderating temperature swings. Islands in tropical waters stay pleasant even when nearby continents bake. Inside your body, the high heat capacity of water helps maintain stable temperature. You are mostly water, and this water acts as a thermal buffer, preventing dangerous fluctuations. The same property makes water excellent for cooling everything from car engines to nuclear power plants. No other common liquid can match water's ability to absorb heat. Water is sometimes called the universal solvent. Water dissolves more substances than any other liquid. This is why natural water is never truly pure. It always carries dissolved minerals, gases, and organic compounds. The secret lies in water's molecular structure. Each water molecule has a slight positive charge on one side and a slight negative charge on the other. This polarity allows water to pull apart ionic compounds like salt and interact with many other molecules. This dissolving power makes water essential for life. Nutrients, minerals, and oxygen dissolve in water and travel through ecosystems. Inside cells, dissolved chemicals react with each other to sustain metabolism. But water's solvent power also means it can carry pollutants, making water quality a critical concern for health and environment. Pure water does not conduct electricity well. Despite what you might have heard about the dangers of electricity near water, absolutely pure water is actually a poor conductor. It contains almost no free ions to carry electrical current. The water that conducts electricity is water with dissolved substances in it. Salt, minerals, and other impurities provide the ions that allow current to flow. This is why ocean water and tap water can be dangerous around electricity, while distilled water is relatively safe. In laboratories, scientists can produce ultra-pure water that barely conducts at all, but this water is unstable. it immediately begins absorbing carbon dioxide from the air, which dissolves to form carbonic acid and create ions. In nature, water almost always contains enough dissolved substances to conduct some electricity. Water molecules stick together through hydrogen bonding. The positive end of one water molecule is attracted to the negative end of another. These connections, called hydrogen bonds, link water molecules together in a constantly shifting network. Each hydrogen bond is weak, but there are so many of them that together they give water remarkable properties: surface tension, high heat capacity, and the ability to climb through thin tubes all result from hydrogen bonding. The bonds form and break trillions of times per second. In liquid water, each molecule is connected to an average of about 3.4 other molecules at any moment. This number decreases as temperature rises. When water freezes, the hydrogen bonds become fixed in a rigid pattern, creating the crystalline structure of ice. Water can absorb many wavelengths of light. When sunlight enters water, some wavelengths are absorbed more quickly than others. Red light disappears first, followed by orange and yellow. Blue and green penetrate deepest, which is why deep water appears blue. At about 200 meters, almost all light has been absorbed. Below this depth lies a realm of perpetual darkness, illuminated only by bioluminescent creatures. This selective absorption also explains why underwater photography taken without flash have a blue or green tint. The missing red wavelengths must be added artificially. Light and water interact in ways that color our perception of oceans, lakes, and pools. Water reflects light and creates rainbows. When sunlight passes through water droplets in the air, it separates into its component colors. Each droplet acts as a tiny prism, bending red light less than violet. Rainbows appear when conditions allow millions of droplets to reflect and refract light back toward your eyes. The arc shape results from the geometry of light bouncing inside spherical drops. Double rainbows occur when light reflects twice inside each droplet. The second rainbow appears above the first, with colors reversed. These familiar arcs of color demonstrate the intimate dance between light and water. Mirages are caused by light bending through heated air. On hot days, the air just above the ground becomes warmer and less dense than the air above it. Light traveling through this temperature gradient bends, creating shimmering illusions. The classic desert mirage makes the road ahead appear wet, reflecting the sky like a pool of water. This illusion is particularly cruel in environments where real water is desperately needed. Superior mirages occur when cold air sits beneath warm air, bending light downward. These can make distant ships appear to float above the horizon or stretch into impossible shapes. Air, heat, and light conspire to create visions of water that do not exist. Water expands when heated and when frozen. Most substances simply expand when heated and contract when cooled. Water does this too, but only above about 4 degrees Celsius. Below this temperature, water begins to expand as it cools, reaching maximum density at 4 degrees. This is why the bottom of a lake in winter is warmer than the surface. This strange physics of cold water has profound consequences for aquatic life. Water has the highest specific heat of any common substance. Specific heat measures how much energy is needed to raise a substance's temperature. Water requires more energy than almost any other material. This means water heats slowly and cools slowly. It acts as a thermal flywheel, storing heat and releasing it gradually. The oceans store enormous amounts of heat, absorbing energy from the sun during the day and in summer, then releasing it slowly. This moderates temperature extremes on land and regulates global climate. The same property allows water to protect living tissues from sudden temperature changes. Water has the highest surface tension of any common liquid except mercury. Fill a glass slightly above the rim and watch the water bulge upward without spilling. This is surface tension at work, creating an invisible elastic skin on the water's surface. Surface tension results from hydrogen bonds pulling water molecules toward each other. At the surface, molecules are pulled inward and sideways, but not upward, creating tension. This property allows some insects to walk on water. Water striders have legs coated with waxy hairs that resist getting wet, allowing them to stand on the surface film without breaking through. Surface tension also helps water climb through thin tubes and move through soil. It shapes raindrops into spheres and allows soap bubbles to form. Raindrops are not shaped like teardrops. Despite what artists often draw, falling raindrops are not teardrop-shaped. Small raindrops are almost perfectly spherical, shaped by surface tension pulling them into the most compact form. Larger raindrops flatten on the bottom as they fall, becoming more like hamburger buns. Very large drops oscillate between shapes before eventually breaking apart into smaller droplets. The largest raindrops can reach about 5 millimeters in diameter before air resistance tears them apart. Drops larger than this are unstable and split into smaller pieces. The classic teardrop shape exists only in special circumstances, such as water dripping slowly from a faucet before it detaches. It takes enormous energy to turn liquid water into steam. Boiling water requires far more energy than simply heating it. This extra energy, called the latent heat of vaporization, breaks hydrogen bonds that hold water molecules together. This is why sweating cools you down so effectively. As sweat evaporates from your skin, it carries away a large amount of heat. The energy used to break those molecular bonds comes from your body. Steam burns are more severe than hot water burns, partly because of this stored energy. When steam condenses on your skin, it releases all that latent heat at once. This same property is why steam engines were so powerful. The energy stored in steam could drive machinery far more efficiently than simply heating water. The deepest point in the ocean is nearly 7 miles down. At the bottom of the Mariana Trench in the Pacific Ocean lies Challenger Deep, the lowest point on Earth's surface. It reaches down about 36,000 feet, or nearly 7 miles. If Mount Everest were placed in the Mariana Trench, its peak would still be more than a mile underwater. The pressure at the bottom is over 1,000 times greater than at the surface. Yet, even in this extreme environment, life exists. Scientists have found fish, shrimp-like amphipods, and vast communities of bacteria living in the crushing darkness. Challenger Deep was first reached by humans in 1960 when Jacques Piccard and Don Walsh descended in the bathyscaphe Trieste. More people have walked on the moon than have visited the deepest point in the ocean. Ocean water contains about 3.5% salt. The saltiness of seawater has remained relatively stable for hundreds of millions of years. Rivers continuously carry dissolved minerals from land to the sea, but this input is balanced by processes that remove salt. If you could evaporate all the water from the oceans, the remaining salt would cover the continents to a depth of about 500 feet. The oceans contain an almost unimaginable amount of dissolved material. The most common salt is sodium chloride, ordinary table salt, but seawater also contains magnesium, sulfur, calcium, potassium, and traces of virtually every natural element. This mineral content makes seawater undrinkable for humans, but it provides essential nutrients for marine life. The ocean contains over 90% of all living space on Earth. When we calculate the volume of habitat available for life, the ocean dominates completely. Land habitats are essentially thin films on the planet's surface, while the ocean provides vast three-dimensional space for organisms. Most of this space is the deep sea, a realm of perpetual darkness, near freezing temperatures and crushing pressure. Yet life thrives there, from microscopic bacteria to giant squid. We have explored only a tiny fraction of the deep ocean. New species are discovered regularly, and scientists estimate that millions of marine species remain unknown to science. The ocean remains Earth's greatest unexplored frontier. Ocean currents move more water than all the world's rivers combined. The Gulf Stream alone transports about 30 times more water than all the rivers on Earth put together, and the Gulf Stream is just one of many major ocean currents. These currents form a global conveyor belt that redistributes heat around the planet. Warm water flows toward the poles at the surface, cools, and sinks. Cold water then flows back toward the equator in the depths. This circulation takes about 1,000 years to complete one full cycle. It influences climate patterns, marine ecosystems, and even the distribution of nutrients in the ocean. Changes in ocean circulation could have dramatic effects on global climate. The mid-ocean ridges form the longest mountain chain on Earth. Running through all the world's oceans is a continuous chain of underwater mountains stretching over 40,000 miles. This is longer than all the mountain ranges on land combined. At the mid-ocean ridges, tectonic plates are pulling apart. Magma rises from below to fill the gap, creating new ocean floor. This process has been building and reshaping the ocean basins for billions of years. The ridges are sites of intense geological activity with volcanic eruptions and hydrothermal vents that support unique ecosystems. Life thrives in these harsh environments, far from sunlight. The mountains are largely hidden from view, but they represent one of Earth's most dynamic geological features. Hydrothermal vents support life without sunlight. Deep in the ocean, where no light penetrates, communities of organisms thrive around volcanic vents. Superheated water, rich in chemicals, streams up from below the seafloor. Instead of photosynthesis, these ecosystems rely on chemosynthesis. Bacteria use the chemical energy from hydrogen sulfide and other compounds to produce food. Other organisms then feed on these bacteria. Giant tube worms, eyeless shrimp, and ghostly fish cluster around the vents. Some of these creatures are found nowhere else on Earth. The discovery of vent communities in 1977 revolutionized our understanding of where life can exist. It suggested that life might be possible in similar environments on other worlds. Some deep-sea fish produce their own light. In the dark depths of the ocean, many creatures have evolved bioluminescence. They use chemical reactions to produce light for hunting, communication, and defense. Anglerfish dangle glowing lures to attract prey. Flashlight fish use light organs to navigate and find food. Some species produce sudden flashes to startle predators. Bioluminescence is so common in the deep sea that it may be the most widespread form of communication on Earth. An estimated 90% of deep-sea animals can produce light. This living light comes in many colors, though blue and green are most common because these wavelengths travel farthest through seawater. The ocean absorbs about 1/4 of human carbon dioxide emissions. Every year, the ocean dissolves billions of tons of carbon dioxide from the atmosphere. This has helped slow the pace of climate change, but it comes with a cost. When carbon dioxide dissolves in seawater, it forms carbonic acid, which is gradually making the ocean more acidic, a process called ocean acidification. Since the Industrial Revolution, ocean acidity has increased by about 30%. This threatens organisms that build shells and skeletons from calcium carbonate, including corals, mollusks, and some plankton. The ocean's role as a carbon sink is vital for regulating climate, but its capacity has limits. Waves can travel thousands of miles across open ocean. Storm waves generated in one part of the ocean can travel vast distances before reaching shore. Swells from storms in the Southern Ocean regularly reach beaches in California and Hawaii. As waves travel, they sort themselves by wavelength. Longer waves move faster and arrive first, followed by progressively shorter waves. This is why the first swells from a distant storm are long and rolling. Waves do not actually move water across the ocean. Instead, energy passes through the water while the water itself moves in circular orbits. A floating object bobs up and down, but barely moves horizontally. Only near shore, where waves feel the bottom, does water actually move forward in the breaking waves. Tsunamis can cross entire oceans in hours. Unlike ordinary wind waves, tsunamis are generated by earthquakes, volcanic eruptions, or underwater landslides. The disturbance moves the entire water column from surface to seafloor. In deep water, tsunamis travel at the speed of a jet airplane, over 500 miles per hour, but they are only a few feet high and pass unnoticed by ships at sea. As a tsunami enters shallow water, it slows down and the energy compresses. The wave height grows dramatically, sometimes reaching 100 feet or more. Pacific Island cultures preserved oral histories of great waves for generations, warning descendants of dangers that might come from the sea. Groundwater is the largest reservoir of liquid fresh water. While we often think of rivers and lakes when we picture fresh water, the vast majority of liquid fresh water is actually underground. Groundwater makes up about 30% of all fresh water, compared to less than 1% in surface water. This water fills spaces between soil particles and flows through cracks in rock. It can remain underground for days, years, or even thousands of years before emerging in springs or being pumped up through wells. Aquifers, underground layers of rock or sediment that hold water, supply drinking water to billions of people worldwide. Some aquifers are being depleted faster than rainfall can recharge them. The water deep underground is often ancient, sealed away since long before human civilization began. The largest known underground lake lies beneath the Congo. Scientists have discovered evidence of vast reservoirs of water deep within the earth. Beneath the Democratic Republic of the Congo, researchers believe there may be enormous underground water reserves. These discoveries are part of growing evidence that Earth's interior contains far more water than previously thought. Water is locked within minerals deep in the mantle, and some of it forms subterranean reservoirs. Similar underground water has been found beneath the driest deserts. Libya's great man-made river taps ancient aquifers dating back to when the Sahara was green with lakes and vegetation. The water cycle extends far deeper than the surface we see. Some caves contain underground rivers and lakes. Water has carved extraordinary networks of caves through soluble rocks like limestone. Underground rivers flow through these hidden passages, sometimes for miles. The longest underwater cave system explored so far is the Sistema Sac Actun in Mexico, with over 200 miles of surveyed passages. Much of this system remains underwater, explored only by specialized cave divers. These underground waters often support unique ecosystems. Blind cave fish and translucent crayfish have evolved in the darkness, losing their pigments and eyes over millions of years. The caves also preserve remarkably pure water, filtered slowly through rock over centuries. Hot springs occur where groundwater meets volcanic heat. When groundwater seeps down and encounters hot rock, it heats up and often returns to the surface as a hot spring. These thermal waters have attracted humans for thousands of years. The minerals dissolved in hot spring water depend on the local geology. Some springs deposit colorful minerals around their edges. Others contain sulfur compounds that smell like rotten eggs. Yellowstone National Park contains more than 10,000 hot springs, geysers, and other thermal features. The heat comes from a massive magma chamber beneath the park. Many cultures have revered hot springs as sacred healing places. Old Faithful erupts because of underground plumbing. Geysers are rare phenomena that require a specific combination of heat, water, and underground geology. Water must be able to circulate through constricted channels that allow pressure to build. At Old Faithful in Yellowstone, water seeps down and is heated beyond boiling, but the pressure from water above prevents it from turning to steam immediately. When pressure finally overcomes the water above, the geyser erupts. After an eruption, the chamber refills with water and the process begins again. Old Faithful erupts about every 90 minutes, though the interval varies depending on how much water was released. There are fewer than 1,000 active geysers in the world, and most are in Yellowstone, Iceland, and New Zealand. The Great Lakes contain 20% of the world's surface freshwater. Formed by retreating glaciers about 10,000 years ago, the 5 Great Lakes of North America hold an enormous volume of water. Only the polar ice caps and Lake Baikal in Russia contain more freshwater. The lakes are so large that they have measurable effects on regional climate. Lake effect snow dumps enormous amounts of precipitation on nearby land. The lakes also moderate summer and winter temperatures. About 30 million people depend on the Great Lakes for drinking water. The lakes also support commercial fishing, shipping, and recreation. It would take about 200 years for the Great Lakes to completely refill if they were somehow emptied. Lake Baikal holds more water than all the Great Lakes combined. Nestled in Siberia, Lake Baikal is the deepest and oldest lake on Earth. It reaches depths of over 5,000 feet and contains about 22% of the world's surface freshwater. The lake formed in a rift valley about 25 million years ago and has been filling with water ever since. Some of the water at the bottom may have been there for hundreds of thousands of years. Baikal supports unique species found nowhere else, including the world's only freshwater seal. The lake's extreme age has allowed evolution to produce an entire ecosystem of endemic organisms. The water is remarkably clear and pure, filtered by tiny crustaceans that consume algae and bacteria. The Dead Sea is so salty that nothing can sink in it. At over 400 meters below sea level, the Dead Sea is the lowest point on Earth's surface. The Jordan River flows in, but there is no outlet. Water can only leave by evaporation, leaving behind dissolved minerals. The salt concentration is about 10 times higher than ordinary seawater. This makes the water so dense that humans float effortlessly without any effort. The high salinity makes the Dead Sea hostile to most life, hence its name. Only a few species of bacteria and algae can survive in its waters. The Dead Sea is shrinking as the Jordan River is diverted for irrigation, leaving behind expanding salt flats. Antarctica contains about 70% of Earth's freshwater. The ice sheet covering Antarctica is over a mile thick on average and nearly 3 miles thick in some places. If it all melted, global sea levels would rise by about 190 feet. This ice has accumulated over millions of years, layer upon layer of compressed snow. Ice cores drilled from the sheet contain bubbles of ancient atmosphere, allowing scientists to study past climates. The ice flows slowly toward the coast, where it breaks off as icebergs. Some Antarctic icebergs are larger than small countries. Despite holding most of Earth's freshwater, Antarctica is technically a desert. Very little new snow falls each year, but the air is so cold that almost none melts. Glaciers move slowly, but reshape landscapes dramatically. Glaciers are rivers of ice that flow under their own weight. The flow is usually imperceptible, measured in feet per year, but the effects accumulate over millennia. As glaciers advance, they carve distinctive valleys with U-shaped profiles. They pluck rocks from mountain walls and push debris ahead of them like bulldozers. When glaciers retreat, they leave behind a transformed landscape. Moraines mark where ice once reached. Lake basins fill the hollows carved by ice. Polished rocks show where glaciers passed. During ice ages, glaciers covered much of North America and Europe. Their legacy is written across the landscape.
Sea ice forms differently from freshwater ice. When seawater freezes, the salt is largely excluded from the ice crystals. This creates pockets of concentrated brine within the ice structure. The brine gradually drains out, so older sea ice is less salty than new ice. Sea ice is also more pliable than freshwater ice. It can bend with waves and flex without breaking. This flexibility allows polar bears and seals to walk on ice that would crack immediately in a frozen lake. The Arctic Ocean freezes over every winter, with ice extent reaching its maximum in March. In summer, much of this ice melts, though some multi-year ice persists. Climate change is dramatically reducing Arctic sea ice extent and thickness. Icebergs can be enormous and persist for years. When glaciers reach the sea, chunks break off to become icebergs. Antarctic icebergs can be tabular, flat-topped sheets of ice hundreds of square miles in size. Only about 10% of an iceberg is visible above water. The rest lurks below the surface, a hazard to ships. The iceberg that sank the Titanic had drifted south from glaciers in Greenland. Large icebergs can survive for years, drifting with ocean currents. They gradually melt and break apart, releasing fresh water into the sea. Scientists track icebergs by satellite, both for shipping safety and to understand how ice sheets are changing. Clouds form when water vapor condenses around tiny particles. For water vapor to condense into droplets, it needs something to condense onto. These condensation nuclei can be dust, pollen, sea salt, or even pollution particles. Without these nuclei, the air could become supersaturated with water vapor without forming clouds. The particles provide surfaces where water molecules can gather and droplets can grow. Cloud droplets are incredibly small, typically about 20 micrometers in diameter. 1 million of them might fit in a single raindrop. Different types of clouds form at different altitudes and temperatures, from low-lying fog to towering thunderheads reaching miles into the sky. One cloud can weigh millions of pounds. Though clouds appear light and fluffy, they contain enormous amounts of water. A typical cumulus cloud might contain several hundred tons of water droplets. The droplets remain suspended because they are so small that air resistance prevents them from falling. It takes many collisions between droplets to form raindrops heavy enough to fall. Large storm clouds can contain billions of tons of water. When this water falls as rain or hail, the energy released can power violent weather. The water in clouds comes from evaporation below. Warm, moist air rises, cools, and its water vapor condenses to form the visible cloud. Fog is simply a cloud at ground level. When conditions are right, clouds can form at the Earth's surface instead of in the sky. This ground-level cloud is what we call fog. Fog often forms on clear, calm nights when the ground cools rapidly and chills the air above it. It can also form when warm, moist air flows over cooler water or land. San Francisco is famous for its fog, which forms when warm air from inland flows over the cold California current. The fog pours through gaps in the coastal hills like water. Fog can persist for hours or days until wind or sunshine disperses it. Dew forms when surfaces cool below the dew point. On clear nights, objects near the ground lose heat by radiation and become cooler than the surrounding air. When they cool below the dew point,
water vapor condenses on their surfaces. The dew point is the temperature at which water vapor becomes saturated with water vapor. Below this temperature, excess moisture must condense out. Dew often forms on grass because the thin blades cool quickly and have large surface areas. Cars and windows also collect dew on cool mornings. In some dry regions, fog and dew are important sources of moisture for plants and animals. Frost is not frozen dew. Although frost and dew both form by condensation, frost is not simply dew that is frozen. Frost forms when water vapor changes directly from gas to solid ice crystals, skipping the liquid phase entirely. This process, called deposition, occurs when the surface temperature is below freezing. The ice crystals grow outward from the surface in intricate patterns. Frost can form even when air temperature is above freezing if the surface itself is cold enough. This is why frost sometimes appears on cars and windows when the official temperature reads above 32 degrees Fahrenheit. The delicate crystal structures of frost are shaped by temperature and humidity as they form. Snow crystals come in endless varieties. Every snow crystal begins as a tiny hexagonal plate forming around a microscopic particle. As the crystal falls through the cloud, it encounters varying conditions that shape its growth. Temperature and humidity determine whether the crystal grows into plates, columns, needles, or the classic six-armed dendrites. Even small variations produce different patterns. Wilson Bentley, a Vermont farmer, was the first to photograph snow crystals in 1885. He captured over 5,000 images, each one unique. While the saying that no two snowflakes are alike may be technically unprovable, the number of possible arrangements is so vast that identical crystals are essentially impossible. Hail forms in powerful thunderstorms. Hailstones grow in the intense updrafts of severe thunderstorms. A small ice pellet is carried upward by rising air, accumulates a layer of ice, falls, and is caught by the updraft again. Each cycle adds a new layer. Cutting a hailstone in half often reveals onion-like rings showing its history of trips up and down through the storm. The largest hailstone ever recorded in the United States fell in South Dakota in 2010. It measured about 8 inches in diameter and weighed nearly 2 pounds. Hail causes billions of dollars in damage each year to crops, vehicles, and buildings. Lightning superheats the air and creates thunder. A lightning bolt can heat the air along its path to about 30,000 degrees Kelvin, 5 times hotter than the surface of the sun. This rapid heating causes the air to explode explosively, producing thunder. Light travels almost instantaneously, but sound takes about 5 seconds to travel a mile. By counting the seconds between lightning and thunder, you can estimate how far away the storm is. Thunder rumbles rather than popping because lightning follows a long, jagged path. Sound from different parts of the bolt arrives at different times. Lightning can strike the same place repeatedly. Tall structures like the Empire State Building may be struck dozens of times per year. The water cycle connects all Earth's systems. Evaporation, condensation, precipitation, and runoff form a continuous cycle that moves water around the planet. Energy from the sun drives this cycle, lifting water from the surface into the atmosphere. The cycle operates on many timescales. A water molecule might evaporate from the ocean and fall as rain within days, or it might remain frozen in a glacier for thousands of years before melting and reaching the sea. Human activities have begun to alter parts of the water cycle. Irrigation moves water from underground to the surface. Dams interrupt the flow of rivers. Land use changes affect how much water soaks in versus running off. Understanding the water cycle is essential for managing water resources in a changing climate. An average person uses about 80 to 100 gallons of water daily. Most of this water goes to bathing, flushing toilets, washing clothes and dishes, and watering lawns. only a tiny fraction is actually consumed as drinking water. Indoor water use has declined in recent decades as toilets, shower heads, and appliances have become more efficient, but outdoor water use, especially for irrigation, remains high. The water we use does not disappear. It returns to the environment through sewage treatment or evaporation, but withdrawing water faster than natural systems can replenish it depletes aquifers and rivers. Water conservation reduces energy use too, since pumping and treating water requires significant electricity. Agriculture uses about 70% of global freshwater withdrawals. Growing crops requires enormous amounts of water. A single hamburger requires about 660 gallons of water when you account for watering the grain to feed the cattle. Rice paddies, cotton fields, and irrigated orchards consume vast quantities of water. In dry regions, irrigation water often comes from aquifers that are being depleted. As the global population grows and diets change, agricultural water demand is increasing. Finding ways to grow more food with less water is one of the great challenges of our time. Drip irrigation, drought-resistant crops, and improved farming practices can help reduce agricultural water use. Desalination can make seawater drinkable. With most of Earth's water locked in salty oceans, turning seawater into fresh water has long been a dream. Modern desalination plants make this possible, though at significant cost. Most desalination works by reverse osmosis, forcing seawater through membranes that filter out salt and other dissolved substances. The process requires substantial energy. The Middle East leads the world in desalination, with Saudi Arabia producing billions of gallons of fresh water from seawater each year. Coastal cities worldwide are increasingly turning to desalination as other sources become strained. The concentrated brine left over from desalination poses environmental challenges when discharged back to the sea. Water quality affects the health of billions. Access to clean drinking water is not universal. Nearly 1 billion people lack access to safe water, and billions more drink water that may contain harmful contaminants. Waterborne diseases like cholera, typhoid, and dysentery still kill hundreds of thousands of people each year, mostly children in developing countries. Even in wealthy countries, aging infrastructure can compromise water quality. Lead from old pipes, agricultural runoff, and industrial pollution threaten water supplies. Protecting water quality requires investment in treatment, infrastructure, and preventing pollution at its source. Wetlands filter water naturally. Marshes, swamps, and other wetlands act as natural water treatment systems. As water flows slowly through wetland vegetation, sediments settle out and plants absorb nutrients and pollutants. Wetlands also store water during floods and release it slowly during dry periods. They protect coastlines from storm surges and provide habitat for countless species. For centuries, wetlands were drained for agriculture and development. More recently, their value has been recognized, and restoration efforts are underway in many areas. Constructed wetlands now treat wastewater in some communities, harnessing natural processes to clean water. Rivers have carved some of Earth's most spectacular landscapes. The Grand Canyon, carved by the Colorado River over millions of years, is one of Earth's most dramatic examples of water's erosive power. The canyon is over a mile deep and exposes rocks nearly 2 billion years old. Rivers carve canyons by dissolving rock, carrying away sediments, and abrading surfaces with the sand and pebbles in their flow. Given enough time, even hard rock yields to flowing water. The world's rivers move billions of tons of sediment each year from land to sea. This sediment builds deltas and replenishes beaches. The landscapes we see today are largely the work of water, patient and persistent over geological time.
Waterfalls occur where rivers encounter resistant rock. When a river flows over an edge of hard rock underlain by softer rock, the softer material erodes faster, creating a steep drop. Over time, the waterfall may retreat upstream as the edge erodes. Niagara Falls retreats about 1 foot per year. Since the last ice age, the falls have moved several miles upstream from their original position. The tallest waterfall on land is Angel Falls in Venezuela, dropping 3,212 feet. Much of this height is free fall, with water turning to mist before reaching the bottom. Underwater waterfalls also exist, where dense cold water plunges down underwater slopes. Waterfalls generate negative ions that may affect mood. The crashing water at waterfalls produces negative ions, electrically charged particles that some research suggests may have mild positive effects on mood and well-being. The same effect occurs at beaches, in thunderstorms, and after rain. Whether negative ions directly affect health or if simply being near water provides psychological benefits is unclear. Regardless of the mechanism, humans have long been drawn to waterfalls. Their power, beauty, and the sound of rushing water create a sense of awe that transcends any specific health effect. Waterfalls appear in art, mythology, and dreams as symbols of transformation and natural power. The sound of water is naturally calming to many people. The gentle sound of rain, flowing streams, or ocean waves is a popular choice for relaxation and sleep. Research confirms that water sounds can reduce stress hormones and promote relaxation. These sounds may be partly because they are non-threatening background noise that masks more startling sounds. Constant, predictable sounds allow the brain to relax. Humans may also have an evolutionary affinity for water sounds. Access to water meant survival for our ancestors, so the sound of flowing water might signal safety. Whatever the reason, the sound of water remains one of nature's most reliable paths to peace.
Babies develop an amniotic fluid. For the first 9 months of every human life, we float in water. The amniotic fluid that fills the womb cushions the developing baby, maintains stable temperature, and allows free movement. The composition of amniotic fluid changes throughout pregnancy. Early on, it is mostly water from the mother's body. Later, the baby contributes by swallowing and excreting the fluid. This watery environment may explain why the sound of flowing water calms so many people. It echoes the first environment we ever knew. Our connection to water begins before we take our first breath. The human brain can sense dehydration before you feel thirsty. Specialized neurons in the brain monitor blood concentration and trigger the sensation of thirst. But the brain also uses learned behaviors to anticipate water needs. Research shows that the brain begins preparing the body for hydration as soon as you start drinking, before the water has even reached the bloodstream. Thirst diminishes within seconds of drinking. This anticipatory system prevents over-drinking. If we relied only on measuring blood concentration, we would drink far more than needed before the signal caught up. The brain's relationship with water is sophisticated and forward-looking. Different foods contain widely varying amounts of water. While beverages are the obvious source of hydration, solid foods contribute significantly to water intake. Many fruits and vegetables are over 90% water by weight. Watermelons, cucumbers, and lettuce are among the most water-rich foods. Even bread contains about 30% water, and meat can be over 50%. In some cultures, much of daily water intake comes from food rather than drinks. Soups, stews, and fresh produce can provide substantial hydration. Every meal is an opportunity to replenish the water your body needs. Water intoxication is rare but dangerous. While dehydration is far more common, drinking too much water too quickly can be harmful or even fatal.
This condition, called hyponatremia, occurs when excess water dilutes the sodium in blood to dangerous levels. The brain is particularly sensitive to sodium imbalance. Severe hyponatremia can cause confusion, seizures, and swelling of the brain. Most cases occur in endurance athletes who drink large amounts of water during long events. Normal drinking behavior rarely causes problems. Like most things in life, balance is essential. Neither too little nor too much water is healthy. Camels store fat, not water, in their humps. The common belief that camel humps store water is a myth. The humps contain fat reserves that provide energy when food is scarce. Camels are adapted to conserve water in other ways. Their kidneys produce highly concentrated urine, their noses recapture moisture from exhaled breath, and they can tolerate wide swings in body temperature. When camels do drink, they can consume over 20 gallons in just a few minutes. Their oval-shaped blood cells can swell to accommodate the influx without bursting. These remarkable adaptations allow camels to survive in some of the driest places on Earth. Desert plants have evolved remarkable water-saving strategies. Cacti store water in their thick stems and have waxy coatings that prevent evaporation. Their spines are actually modified leaves that reduce surface area and water loss. Some desert plants close their stomata during the day and open them at night when temperatures are cooler. Others have extremely deep root systems that tap groundwater far below the surface. The creosote bush can survive years without rain by dropping its leaves and going dormant. When rain finally comes, it quickly springs back to life. Life finds ways to persist even where water is scarce. The driest desert on Earth is in Antarctica. The McMurdo Dry Valleys in Antarctica receive almost no precipitation and have not seen rain or snow for millions of years. Strong winds evaporate any moisture before it can accumulate. Even though the cold, these valleys are deserts in the truest sense. The ground is completely dry, and only the hardiest microbes survive in the extreme conditions. Scientists study the dry valleys as analogs for Mars and other planets where life might exist in extremely arid, cold conditions. Even on a planet dominated by water, truly dry places exist. Every living cell on Earth contains water, from bacteria to blue whales, from desert plants to deep-sea worms. Every cell requires water to function. Cells are essentially tiny bags of water with molecular machinery dissolved and suspended within. Water provides the medium for biochemical reactions. Nutrients, waste products, and signaling molecules all move through the watery interior of cells. The percentage of water varies by organism and tissue. Jellyfish are over 90% water. Human bodies are about 60% water, with brains and kidneys containing more than muscles or bones. Life as we know it cannot exist without water. Plants transport water from roots to leaves through capillary action. The narrow vessels inside plant stems act like tiny tubes, and water rises through them partly through capillary action. The cohesion of water molecules and their adhesion to vessel walls pulls water upward. This mechanism can lift water hundreds of feet in the tallest trees. The process is driven by evaporation from leaves, which creates a pull that draws water up from the roots. The same forces that create surface tension allow water to defy gravity within plant tissues. The hydrogen bonds between water molecules form an unbroken chain from root to leaf. Without this mechanism, there would be no tall trees and no leaves waving in the breeze. Trees release water vapor through transpiration. As water evaporates from leaf surfaces, it draws more water up through the plant. A large tree can transpire hundreds of gallons of water on a hot summer day. This water vapor rises into the atmosphere and can travel far from its source before condensing as clouds and falling as rain. The Amazon rainforest
creates much of its own rainfall through transpiration. Forest loss can disrupt regional water cycles. Deforestation reduces transpiration, potentially leading to drier conditions downwind. Trees are water pumps, moving water from the ground to the atmosphere and helping to drive weather patterns. Your body is about 60% water by weight. The exact percentage varies by age, sex, and body composition. Babies have the highest water content, about 75%. Older adults may be closer to 50%. Water performs countless functions in the body. It carries nutrients and oxygen to cells, removes waste, lubricates joints, cushions organs, and regulates temperature. Losing just 2% of your body's water can impair physical and mental performance. Severe dehydration is life-threatening. We continuously lose water through breath, sweat, and elimination, requiring constant replacement through food and drink. Blood is mostly water. Blood plasma, the liquid portion of blood that carries red blood cells and white blood cells, is about 92% water. This watery medium allows blood to flow smoothly through vessels. The water in blood helps regulate body temperature. When you are hot, blood vessels near the skin dilate, allowing heat to escape. When you are cold, they constrict to conserve heat. Blood also carries dissolved gases. Oxygen binds to hemoglobin in red blood cells, while carbon dioxide dissolves directly in plasma. The seemingly simple presence of water enables all of blood's complex functions. Your brain is about 75% water. The brain floats in cerebral spinal fluid, cushioned and protected by water. Even mild dehydration can affect cognitive function, causing difficulty concentrating and impaired short-term memory. The water in brain tissue allows electrical signals to propagate between neurons. Ion channels open and close, allowing charged particles to flow through the watery medium inside and outside cells. Staying hydrated supports clear thinking. When you feel mentally foggy, a glass of water may help. The intimate connection between water and thought reminds us how physical and mental well-being are intertwined. Tears are mostly water, with dissolved salts and proteins. Emotional tears differ slightly in composition from tears that form to protect the eyes from irritants. Emotional tears may contain higher levels of stress hormones and natural painkillers. Crying may help regulate emotions, partly by releasing these compounds. The act of crying itself may provide comfort through its social signals and physical release. Basal tears, the constant film of moisture on your eyes, keep the cornea healthy and clear. Without this thin layer of water, vision would quickly deteriorate. Each blink spreads a fresh layer of tears across the eye surface.
Humans cannot survive more than a few days without water, while the body can survive weeks without food by metabolizing stored fat. Water loss cannot be compensated from body stores. The body constantly loses water and has no reserve to draw upon. In hot conditions or with physical exertion, survival time without water may be as short as a day. In moderate conditions, most people would not survive more than 3 to 5 days. Thirst is an imperfect signal of hydration status. By the time you feel thirsty, you may already be mildly dehydrated. Access to clean water is truly a matter of life and death. Water was essential for the origin of life. The first living cells almost certainly arose in water, whether in warm pools on early Earth, near hydrothermal vents on the ocean floor, or in other aquatic environments. Water provided the medium for life's chemistry to begin. Water allows organic molecules to interact, form more complex structures, and eventually create self-replicating systems. Without a liquid medium, the chemistry of life could not occur. The search for life elsewhere in the solar system focuses on places where liquid water might exist. Mars once had water. Europa and Enceladus have subsurface oceans. These are prime targets for astrobiology. Where there is water, there is the possibility of life. Water may be surprisingly common in the universe. Astronomers have detected water in interstellar clouds, in the atmospheres of distant planets, and in comets and asteroids throughout our solar system. Water is not rare, but widespread. The hydrogen in water is the most abundant element in the universe. Oxygen is the third most abundant. Their combination to form water seems to occur readily wherever conditions allow. This cosmic abundance of water raises the tantalizing possibility that habitable worlds are common. Galaxies may be dotted with planets where liquid water exists. The water on Earth connects us to a universe that may be full of this remarkable substance. Comets are sometimes called dirty snowballs. The nucleus of a comet is composed largely of water ice mixed with dust and organic compounds. When a comet approaches the sun, the ice vaporizes, creating the spectacular tails that have inspired awe throughout human history. Some of Earth's water may have been delivered by comets bombarding the young planet. The deuterium to hydrogen ratio in some comets matches that of Earth's oceans. Comets are remnants from the formation of the solar system, preserved in deep freeze for billions of years. Studying them reveals the conditions and materials present when our planet was born. Each comet that streaks across the sky carries water that is older than the Earth itself. Mars once had liquid water on its surface. Evidence of ancient rivers, lakes, and possibly oceans covers the Martian surface. Dry channels, layered sediments, and minerals that form only in water tell of a wetter past. Today, Mars is cold and dry, its atmosphere too thin for liquid water to persist on the surface. But water ice exists at the poles and in the soil, and briny liquid may occasionally flow in sheltered locations. The history of water on Mars is a cautionary tale about how planets can lose their habitability. Understanding what happened to Martian water helps us appreciate Earth's good fortune. If life ever arose on Mars, it would most likely have been in the planet's watery youth. Europa's ocean may contain twice as much water as all Earth's oceans. Beneath the icy shell of Jupiter's moon Europa lies a global ocean of liquid water. Tidal forces from Jupiter's immense gravity generate heat that keeps this ocean from freezing solid. The ocean may be in contact with a rocky seafloor where chemical reactions could provide energy for life. Hydrothermal vents, similar to those that support ecosystems on Earth, might exist there. Europa is considered one of the most promising places to search for extraterrestrial life. Future missions may send probes to penetrate the ice and explore the ocean beneath. The possibility that life might exist in Europa's dark waters stirs both scientific curiosity and profound wonder. Comets are sometimes called dirty snowballs. The nucleus of a comet is composed largely of water ice mixed with dust and organic compounds. When a comet approaches the sun, the ice vaporizes, creating the spectacular tails that have inspired awe throughout human history. Some of Earth's water may have been delivered by comets bombarding the young planet. The deuterium to hydrogen ratio in some comets matches that of Earth's oceans. Comets are remnants from the formation of the solar system, preserved in deep freeze for billions of years. Studying them reveals the conditions and materials present when our planet was born. Each comet that streaks across the sky carries water that is older than the Earth itself. Mars once had liquid water on its surface. Evidence of ancient rivers, lakes, and possibly oceans covers the Martian surface. Dry channels, layered sediments, and minerals that form only in water tell of a wetter past.
Today, Mars is cold and dry, its atmosphere too thin for liquid water to persist on the surface. But water ice exists at the poles and in the soil, and briny liquid may occasionally flow in sheltered locations. The history of water on Mars is a cautionary tale about how planets can lose their habitability. Understanding what happened to Martian water helps us appreciate Earth's good fortune. If life ever arose on Mars, it would most likely have been in the planet's watery youth. Europa's ocean may contain twice as much water as all Earth's oceans. Beneath the icy shell of Jupiter's moon Europa lies a global ocean of liquid water. Tidal forces from Jupiter's immense gravity generate heat that keeps this ocean from freezing solid. The ocean may be in contact with a rocky seafloor where chemical reactions could provide energy for life. Hydrothermal vents, similar to those that support ecosystems on Earth, might exist there. Europa is considered one of the most promising places to search for extraterrestrial life. Future missions may send probes to penetrate the ice and explore the ocean beneath. The possibility that life might exist in Europa's dark waters stirs both scientific curiosity and profound wonder.
Enceladus shoots geysers of water into space. Saturn's small moon Enceladus has jets of water vapor and ice particles erupting from its south pole. These geysers shoot material hundreds of miles into space, contributing to one of Saturn's rings. Beneath the ice, Enceladus harbors a global ocean. The Cassini spacecraft flew through the geysers and detected complex organic molecules and hydrogen, suggesting hydrothermal activity on the ocean floor. Like Europa, Enceladus is a prime target in the search for life. The fact that it ejects samples of its ocean into space makes it easier to study than bodies where the ocean is buried deep. These small, icy worlds may be among the most likely places in our solar system to harbor life beyond Earth. Water molecules vibrate and rotate constantly. At the molecular level, water is never still. Molecules spin, twist, and vibrate in response to thermal energy. These motions are what we perceive as heat. The specific frequencies at which water molecules vibrate are unique, like a fingerprint. Infrared light at these frequencies is absorbed by water vapor, which is why water is a greenhouse gas. Even in ice, molecules continue to vibrate, though their positions are fixed in a crystal lattice. Absolute zero, where all motion would cease, has never been reached. The restless motion of water molecules is part of what makes life possible, enabling the chemical reactions that sustain living things. Heavy water contains deuterium instead of ordinary hydrogen. Most hydrogen atoms consist of a single proton, but a small fraction contains a neutron as well. This heavier isotope is called deuterium. Water made with deuterium instead of ordinary hydrogen is called heavy water. It looks and tastes almost the same, but is slightly denser. Large doses of heavy water are toxic because it interferes with cellular chemistry. Heavy water is used in some nuclear reactors and in scientific research. It occurs naturally in ordinary water at a concentration of about 1 part in 6,400. The existence of heavy water reminds us that even the simplest molecule has hidden complexity. Water can exist as a supercritical fluid. At very high temperatures and pressures, the distinction between liquid and gas disappears. Water becomes a supercritical fluid with properties of both states. Supercritical water is an extremely powerful solvent. It can dissolve materials that neither liquid water nor steam could touch. This property is used industrially for processes like cleaning and waste treatment. Supercritical water may exist deep within gas giant planets in zones where pressures and temperatures reach extreme values. The familiar substance in your glass has exotic relatives in environments far removed from everyday experience.
Water has a neutral pH of 7. The pH scale measures how acidic or basic a substance is, ranging from 0 to 14. Pure water sits exactly in the middle, neither acid nor base. This neutral starting point makes water an ideal medium for life. Cells can adjust their internal chemistry in either direction as needed, buffering against harmful changes. Adding a tiny amount of acid or base to pure water changes its pH dramatically because there are so few ions to start with. Natural waters contain dissolved minerals that buffer against pH changes. The neutrality of water provides a stable foundation for the complex chemistry of living systems. Water can remain liquid below its freezing point. Under certain conditions, very pure water can be cooled well below 32 degrees Fahrenheit without freezing. This phenomenon is called supercooling. Supercooled water is unstable. Any disturbance, such as a vibration or contact with a particle, can trigger instant crystallization. The water suddenly freezes into a slush of ice crystals. In clouds, supercooled droplets can exist at temperatures as low as -40 degrees. When ice crystals do form, they grow rapidly at the expense of remaining liquid droplets. This metastable state of water plays important roles in atmospheric science and weather formation. The triple point of water is a fundamental reference in physics. At precisely 0.01 degrees Celsius and 611.657 pascals of pressure, water exists simultaneously as solid, liquid, and gas. This unique point is called the triple point. Scientists use the triple point of water as a fundamental reference for temperature measurements. The Kelvin scale is defined so that the triple point of water is exactly 273.16 Kelvin. At the triple point, you could see ice, water, and water vapor all in equilibrium, each state transforming into the others in a delicate balance. This remarkable condition exists at only one precise combination of temperature and pressure. Water molecules exist for only a millisecond before exchanging atoms. In liquid water, hydrogen atoms constantly hop between neighboring oxygen atoms. A water molecule does not keep the same hydrogen atoms for long. This exchange happens through a process called the Grotthuss mechanism. Protons effectively tunnel through the network of hydrogen bonds, appearing to move faster than individual molecules. This rapid proton hopping is why acids and bases conduct electricity so well in water. The protons can race along chains of water molecules. The water in your glass is a dynamic network of constantly exchanging atoms, not a collection of stable individual molecules. Soap helps water wet surfaces by reducing surface tension. Water's high surface tension prevents it from spreading easily on many surfaces. It beads up instead of forming a thin film. Soap molecules have one end that attracts water and another end that repels it. When soap dissolves in water, these molecules arrange themselves at the surface, disrupting the hydrogen bonding between water molecules. This reduction in surface tension allows soapy water to spread and penetrate into fabrics and between particles of dirt, lifting them away. The chemistry of cleaning depends on modifying water's natural tendency to stick to itself. Insects use surface tension to walk on water. Water striders have long legs covered with tiny hairs coated in waxy substances that repel water. Their weight is distributed across the surface tension film. Each leg creates a tiny dimple in the water surface without breaking through. The surface tension pushes back against this depression, supporting the insect's weight. Water striders can detect vibrations in the surface tension film, sensing both prey and predators. They row across the water using their middle legs while steering with their hind legs. These delicate insects demonstrate how life has evolved to exploit water's unique physical properties. Certain spiders create underwater air bubbles to breathe. The diving bell spider spends almost its entire life underwater but breathes air. It constructs a dome of silk attached to underwater plants and fills it with air carried from the surface. The air bubble acts like a gill, extracting dissolved oxygen from the water and releasing carbon dioxide. This allows the spider to remain submerged for long periods without surfacing. Inside its bubble, the spider waits for prey, mates, and even lays eggs. The underwater world becomes accessible through this ingenious use of air trapped by surface tension. What seems like a hostile environment becomes home through clever adaptation. Certain beetles carry air bubbles under their wing covers. Aquatic beetles trap a layer of air beneath their hard outer wings. This silvery layer provides oxygen for breathing while underwater. Like the diving bell spider, the air layer functions as a physical gill. Oxygen diffuses into the bubble from the surrounding water as the beetle consumes it. The bubble allows beetles to remain submerged for extended periods without surfacing. Some species can stay underwater almost indefinitely if the water is well oxygenated. These small creatures demonstrate how air-breathing animals can colonize underwater habitats. Fish breathe dissolved oxygen from water. Even though water contains relatively little oxygen compared to air, fish extract what they need using highly efficient gills. Water flows over the gill surfaces in one direction, while blood flows in the opposite direction. This counter-current system maximizes oxygen transfer. By the time water leaves the gills, nearly all its oxygen has been absorbed into the blood. Different fish species have adapted to waters with varying oxygen levels. Some can tolerate oxygen-poor swamps, while others require clear, flowing streams. The gills that make underwater breathing possible are marvels of biological engineering. Marine mammals hold their breath for remarkable periods. Whales, seals, and dolphins are air-breathing mammals that have adapted to life in the ocean. They must return to the surface periodically to breathe. Some species have developed extraordinary breath-holding abilities. Beaked whales have been recorded diving for over 3 hours without breathing. Sperm whales regularly dive for 90 minutes. These mammals have evolved ways to store extra oxygen in their blood and muscles, slow their heart rates while diving, and tolerate carbon dioxide buildup that would be dangerous for humans. Their adaptations show how powerfully evolution can reshape an organism to thrive in water.
Whales and dolphins sleep with half their brain at a time. Aquatic mammals cannot simply fall asleep like land animals. They must consciously control their breathing and maintain enough awareness to surface periodically. To solve this problem, dolphins and some whales engage in unihemispheric sleep. One half of the brain sleeps while the other remains awake and vigilant. This allows them to continue swimming, breathing, and watching for predators while still getting the rest they need. The two brain hemispheres take turns sleeping. Life in water has required even the process of sleep to evolve new forms. Sea otters wrap themselves in kelp to avoid drifting. These charming marine mammals often sleep floating on their backs at the surface. To keep from drifting away while sleeping, they wrap strands of kelp around their bodies. Sea otters also hold hands while sleeping in groups. A raft of otters linked together is less likely to separate while they rest. Their dense fur, the thickest of any mammal, traps air bubbles that provide insulation and buoyancy. They spend considerable time grooming to maintain this vital protective layer. Even in the cold Pacific waters, otters have found ways to rest peacefully. Coral reefs are built by tiny animals. The colorful structures we call coral reefs are actually colonies of tiny animals called coral polyps.
Each polyp is related to jellyfish and anemones. The polyps secrete calcium carbonate to build hard skeletons around themselves. Over thousands of years, generation after generation adds to the reef structure. Coral reefs support an incredible diversity of life, often called the rainforests of the sea. Though they cover less than 1% of the ocean floor, they are home to about a quarter of all marine species. These underwater cities are built one tiny skeleton at a time. Many corals get their color from symbiotic algae. Living inside coral tissues are microscopic algae called zooxanthellae. These algae photosynthesize, producing sugars that feed the coral. The algae also give corals their vibrant colors. Different species of zooxanthellae produce different pigments, creating the rainbow hues of tropical reefs. When corals are stressed by warm water or pollution, they expel their zooxanthellae, leaving the coral white and vulnerable. Without their algae partners, corals can starve. The beauty of coral reefs depends on a delicate partnership between animal and plant. Coral spawning creates underwater snowstorms. Once a year, usually after a full moon, entire coral reefs release eggs and sperm simultaneously. Billions of tiny bundles float upward, creating the appearance of an underwater snowstorm. This mass spawning increases the chances of fertilization. The synchronized timing ensures that eggs from one colony can be fertilized by sperm from another, maintaining genetic diversity. Scientists still do not fully understand how corals coordinate this timing so precisely. Temperature, lunar cycles, and chemical signals all seem to play roles. For one magical night, the reef transforms into a blizzard of new life. Mangrove forests protect coastlines from storms. Mangroves are trees and shrubs that grow in coastal areas where fresh and salt water mix. Their tangled root systems stabilize shorelines and absorb wave energy. During hurricanes and tsunamis, mangroves can significantly reduce the power of storm surges. Communities behind healthy mangrove forests suffer less damage than those along unprotected coasts. Mangrove roots also provide nursery habitat for many fish and invertebrates. The sheltered waters between the roots offer protection from predators. These often overlooked forests perform invaluable services at the boundary between land and sea. Seagrass meadows store carbon and shelter marine life. Underwater meadows of seagrass cover coastal waters around the world. These flowering plants, not seaweed, create important habitats for fish, sea turtles, and dugongs. Seagrass meadows are among the most effective carbon sinks on Earth. They capture carbon dioxide and store it in their roots and the sediments below, potentially for thousands of years. Like mangroves, seagrass stabilizes sediments and protects coastlines from erosion. The loss of seagrass meadows contributes to climate change and degrades coastal ecosystems. These unassuming underwater grasslands deserve more attention and protection. Kelp forests can grow remarkably fast. Giant kelp is one of the fastest growing organisms on Earth. Under ideal conditions, it can grow up to 2 feet per day, quickly forming dense underwater forests. Kelp forests provide habitat for countless species, from tiny invertebrates to sea lions and whales. The complex three-dimensional structure creates zones of light and shadow, current and calm. Sea urchins graze on kelp, and without predators to control them, can transform lush forests into barren urchin barrens. Sea otters, by eating urchins, help maintain healthy kelp ecosystems. The balance of this underwater forest depends on connections between species. The open ocean has distinct zones of life. Scientists divide the ocean into zones based on depth and light penetration. The sunlit surface layer, where photosynthesis occurs, extends down to about 200 meters. Below this lies the twilight zone, where some light penetrates but not enough for plants. Many creatures migrate up and down through this zone daily, feeding in the rich surface waters at night. Deeper still is the midnight zone, a realm of complete darkness. Life here depends on organic matter drifting down from above or on chemical energy from hydrothermal vents. Each zone presents different challenges and opportunities for the creatures that inhabit it. The ocean's twilight zone contains vast biomass. The mesopelagic zone, between 200 and 1,000 meters deep, may contain more fish biomass than all other ocean zones combined. Yet it remains one of the least studied parts of our planet. By day, many fish in this zone hide in the darkness, safe from visual predators. At night, they migrate upward to feed on plankton in surface waters. This daily vertical migration is the largest movement of animals on Earth. Billions of tons of fish, squid, and shrimp rise and fall every 24 hours. The twilight zone is a hidden reservoir of life we are only beginning to understand. Bioluminescent animals light up the deep sea. In the darkness of the deep ocean, many creatures produce their own light. This bioluminescence serves many purposes, from attracting mates to luring prey to confusing predators. Some animals use bioluminescence for counter-illumination, producing light on their undersides that matches the faint light filtering from above. This hides their silhouette from predators below. Others use flashing lights to startle attackers, giving them time to escape. Some squirt bioluminescent fluid as a distraction, the underwater equivalent of a smokescreen. The deep sea glows with countless tiny lights, each one part of a survival strategy. Some deep-sea creatures create their own red light. Most deep-sea animals cannot see red light because it does not penetrate far into the ocean. Some predatory fish have evolved to produce red bioluminescence. This gives them a kind of invisible searchlight. They can illuminate and see prey without alerting other predators or alerting the prey itself. Dragonfish have specialized organs that produce red light and eyes adapted to detect it. They hunt in a spectrum invisible to their victims. Evolution has discovered every possible advantage in the competitive darkness of the deep. Pressure in the deep ocean is immense. At the bottom of the ocean, pressure reaches over 1,000 times atmospheric pressure at the surface. This is enough to crush submarines and all but the most specialized equipment. Yet life thrives at these depths. Deep-sea animals have evolved bodies without air spaces that would be compressed. Their cells contain special molecules that maintain function under extreme pressure. Bringing deep-sea creatures to the surface usually kills them because their bodies are adapted to high pressure. Scientists must use special pressure-maintaining containers to study them alive. The deep ocean is an alien world where the rules of survival are rewritten. The ocean's floor is covered with sediment. Much of the deep ocean floor is blanketed with fine sediment that has drifted down over millions of years. This sediment consists of the remains of microscopic organisms mixed with dust and clay. Some areas are covered with ooze made from the silica shells of diatoms or the calcium carbonate shells of foraminifera. The type of sediment depends on what organisms live in the waters above. Cores drilled from the seafloor reveal layers of sediment recording millions of years of Earth's history. Scientists read these layers like pages in a book. The quiet rain of particles to the seafloor writes a slow record of time. Manganese nodules grow slower than almost anything else. Scattered across large areas of the deep seafloor are dark, lumpy nodules rich in manganese and other valuable metals. These nodules grow as minerals precipitate from seawater onto tiny starting particles.
The growth rate is almost unimaginably slow, just millimeters per million years. A nodule the size of a potato may have taken 10 million years to form. Mining these nodules for their metals would disturb ecosystems that have taken millennia to develop. The very slowness of their formation makes the decision about whether to mine them particularly consequential. Patience beyond human imagination has created these treasures of the deep. Deep sea creatures have surprising lifespans. The extreme conditions of the deep ocean slow metabolism and aging. Some deep sea species live far longer than their shallow water relatives. Orange roughy, a deep sea fish, can live over 100 years. Greenland sharks may survive over 500 years, making them the longest-lived vertebrates known. Some deep-sea corals have been dated at over 4,000 years old. These ancient colonies were growing when the Egyptian pyramids were being built. Time moves differently in the darkness of the deep. Underwater volcanoes create new islands. Volcanic eruptions on the seafloor build mountains that sometimes rise above the waves to become islands. The Hawaiian Islands formed this way over a volcanic hotspot. Underwater eruptions can be explosive when magma meets water, creating clouds of steam and ash, or they can be quiet, with lava flowing along the seafloor and building up slowly. New islands are geologically young and barren, but life colonizes them quickly. Seeds float across the sea, birds bring insects, and gradually ecosystems develop. The ocean both destroys and creates land. Hot springs on land can reach scalding temperatures. Natural hot springs occur where groundwater comes into contact with heat from the Earth's interior. The water that emerges can range from pleasantly warm to dangerously hot. Some hot springs reach temperatures near or above boiling. Bacteria called thermophiles thrive in these extreme conditions, forming colorful mats in the superheated water. The enzymes from these heat-loving organisms have found important uses in biotechnology. Taq polymerase, essential for DNA testing and research, comes from bacteria discovered in Yellowstone hot springs. Even the most extreme environments on Earth harbor life that may benefit humanity. Mineral-rich water creates colorful terraces at hot springs. As hot spring water flows over the surface and cools, it deposits the minerals it carries. Over time, these deposits build up into terraces and mounds. The colors often come from heat-loving microorganisms. Different species thrive at different temperatures, creating bands of color as the water cools along its path. Travertine terraces at places like Pamukkale in Turkey and Mammoth Hot Springs in Yellowstone are among the most beautiful geological formations on Earth. Water, heat, minerals, and life combine to create natural works of art. Some lakes are stratified and rarely mix. In some lakes, layers of different densities stack on top of each other and remain separate for years or even centuries. This stratification can be caused by temperature, salinity, or dissolved gases. In extreme cases, the bottom layer may become anoxic, lacking oxygen. Organic matter that sinks into this layer decomposes only partially, building up over time. Lake Nyos in Cameroon accumulated carbon dioxide in its deep layers until a catastrophic release in 1986 killed over 1,700 people. Engineers have since installed pipes to slowly release the gas. Lakes can seem peaceful while harboring invisible dangers. Some lakes explode. When dissolved carbon dioxide accumulates in deep lake water, it can suddenly release in a limnic eruption. This creates a deadly cloud of gas that suffocates everything nearby. Only 2 lakes are known to have experienced limnic eruptions, Lake Nyos and Lake Manoon, both in Cameroon. Scientists monitor other lakes that may pose similar risks.
The eruption at Lake Nyos created a fountain of water and gas over 300 feet high. The carbon dioxide cloud flowed downhill through valleys, killing people and animals for miles. Water that seems benign can harbor deadly power.
Waterfalls can carve caves behind them. The force of water plunging over a cliff erodes the rock behind and below the falls. Over time, this erosion can hollow out a cave behind the curtain of falling water. Standing behind a waterfall, sheltered from the spray, is one of nature's magical experiences. The light filtering through the water creates a shimmering veil. The caves behind falls eventually grow until the overhanging rock collapses. The waterfall then retreats upstream, starting the process again. Water shapes the land through patient, relentless work. The largest waterfall is actually underwater. In the Denmark Strait between Greenland and Iceland, cold, dense water from the Nordic seas plunges over an underwater cliff. This cataract drops over 11,500 feet, dwarfing any surface waterfall. The Denmark Strait cataract carries about 175 million cubic feet of water per second, many times the flow of all the world's rivers combined. This invisible waterfall is part of the global ocean circulation that moves heat around the planet. It occurs where cold northern waters sink to begin their journey south. The greatest waterfall on Earth is hidden beneath the waves. Rivers carry sediment in suspension, solution, and bedload. The material that rivers transport comes in three forms. Fine particles like clay and silt float suspended in the water, giving many rivers their muddy color. Dissolved minerals and ions travel invisibly in solution. This is how salt reaches the sea and how limestone caves form. Heavier particles roll, slide, and bounce along the riverbed as bedload. During floods, even large boulders can move, grinding against each other and the stream bed. Rivers are conveyor belts moving the substance of continents toward the sea. River deltas form where flowing water meets still water. When a river enters a lake or ocean, it slows down and drops its sediment load. Over time, this sediment builds up into a delta, a fan-shaped deposit that extends into the body of water. Deltas are among the most fertile and densely populated landscapes on Earth. The Nile, Mississippi, Ganges, and Mekong deltas support millions of people. Rising sea levels and reduced sediment supply threaten many deltas. When dams trap sediment upstream, deltas stop growing and may begin to sink and erode. The land at the meeting of river and sea is constantly changing. Some rivers disappear underground. In limestone regions, rivers sometimes vanish into sinkholes, continuing their journey through caves before re-emerging miles away. The Danube River loses about a third of its water through sinkholes near its source. This water travels underground and emerges at springs that feed the Rhine. In some karst landscapes, entire river systems exist underground. Surface valleys may be dry, while hidden rivers flow through caverns below. Water finds its way through any crack or weakness in the rock. Aquifers can span entire continents. The Ogallala Aquifer underlies 8 states in the central United States, covering about 174,000 square miles. It supplies water for agriculture across the Great Plains. This water accumulated over millions of years, and much of it is being used faster than rainfall can replenish it. Some areas have seen water tables drop by over 100 feet. The Great Artesian Basin in Australia is even larger, underlying nearly a quarter of the continent. Water in some parts of this aquifer fell as rain millions of years ago. These underground reservoirs represent irreplaceable resources accumulated over geologic time. Springs emerge emerge where groundwater reaches the surface. A spring forms when the water table intersects the ground surface, or when an impermeable layer forces groundwater to emerge. Springs can range from tiny seeps to massive flows. Silver Springs in Florida discharges about 550 million gallons of water per day. Throughout history, springs have been revered as sacred places. The seemingly magical appearance of water from the earth inspired countless myths and rituals. Springs connect the hidden world of groundwater with the surface streams and rivers we see. Water tables rise and fall with seasons and usage. The water table is not a fixed boundary, but an undulating surface that responds to rainfall, evaporation, and human withdrawals. In areas with heavy groundwater pumping, water tables may drop consistently year after year. This can cause land to subside, damage wells, and allow salt water to intrude into coastal aquifers. Managing groundwater requires understanding these invisible dynamics. Condensation on cold surfaces demonstrates the water cycle. A glass of cold water on a humid day illustrates the same process that forms clouds. Water vapor in the air contacts the cold surface and condenses into liquid droplets. This everyday observation reveals the continuous presence of water vapor in the air around us. Even in seemingly dry conditions, some moisture is always present. The same process creates dew, frost, and the moisture on bathroom mirrors after a shower. Water is constantly moving between vapor and liquid states all around us. The water cycle operates not just in the sky, but at the scale of a cold drinking glass. Humidity affects how we perceive temperature. On humid days, sweat evaporates slowly from the skin, reducing the body's ability to cool itself. This makes hot, humid weather feel more oppressive than dry heat. Conversely, dry air can make cold temperatures feel more tolerable because the body loses less heat through evaporation. But very dry air also desiccates skin and mucous membranes. The heat index combines temperature and humidity to indicate how hot conditions actually feel to the human body. High humidity can make a 90-degree day feel like 100. Our comfort depends not just on how much water is in the air, but on how that moisture interacts with our bodies. Wet bulb temperature sets limits on human survival. If humidity is high enough, the human body cannot cool itself through sweating, no matter how much it perspires. The wet bulb temperature measures this limit. At a wet bulb temperature of 35 degrees Celsius or 95 degrees Fahrenheit, even healthy people resting in the shade will die within hours. Their bodies simply cannot shed heat fast enough. Climate change is increasing the frequency of dangerous wet bulb temperatures in some regions. Parts of the Persian Gulf and South Asia have already experienced conditions approaching this threshold. Water in the atmosphere can determine whether humans can survive in a given climate. Drought is a slow-motion disaster. Unlike earthquakes or hurricanes, droughts develop gradually over months or years. This slow onset can make them harder to recognize and respond to. Droughts begin when precipitation falls below normal for extended periods. Soil moisture declines, streams shrink, and groundwater levels drop. Eventually, agriculture suffers and drinking water supplies become stressed. The effects of drought cascade through ecosystems and economies. Crops fail, livestock die, and people may be forced to migrate. The absence of water can be as devastating as any flood. Flood myths appear in cultures around the world. Stories of great floods that destroyed the world and spared only a few survivors appear in traditions from Mesopotamia to South America, from China to the Pacific Islands. The biblical story of Noah has parallels in the Epic of Gilgamesh and in myths from Greece, India, and countless other cultures. Scholars debate whether these stories recall actual ancient floods.
Some researchers suggest that the flooding of the Black Sea or the end of the last ice age may have inspired some of these legends. Whatever their origins, these stories speak to humanity's deep awareness of water's power to transform the world. Water has shaped human spiritual traditions. Baptism, ritual washing, and sacred rivers appear in religions around the world. Water symbolizes purification, renewal, and the boundary between life and death. The Ganges River is sacred to Hindus who believe bathing in its waters washes away sins. The Jordan River holds similar significance in Christianity. Shinto shrines in Japan always include water for ritual purification. Even secular traditions recognize water's power. We speak of turning over a new leaf, of washing away the past, of emerging clean and refreshed. Water's ability to cleanse and renew has made it a universal symbol of spiritual transformation. The human relationship with water is as old as humanity itself. Our ancestors settled near rivers, lakes, and springs. Water determined where civilizations could arise and flourish. The earliest cities grew along the Tigris, Euphrates, Nile, Indus, and Yellow rivers. Water has shaped human history through droughts and floods, through voyages of exploration across oceans, through the technology of irrigation and aqueducts. We are drawn to water for practical and spiritual reasons. Beaches, riversides, and lake shores remain favorite places for recreation and reflection. The sound of water soothes us. Its presence sustains us. Our bond with water is written deep in our nature.
And so we come to the end of our journey. We have traveled from the cosmic origins of hydrogen and oxygen to the water flowing through your own body. We have explored oceans miles deep and underground rivers never touched by light. We have visited icy moons and ancient comets, waterfalls and storm clouds. Water connects all of these stories. The same substance that fills your cells once drifted between the stars. The rain that falls on your roof carries molecules that have cycled through clouds and oceans for billions of years. As you drift toward sleep, imagine yourself floating in that vast cycle. You are not separate from the waters of the world, but part of them. Every breath you exhale carries moisture back to the atmosphere. Every sip you drink brings the ancient ocean into your body. The water that sustains you has journeyed further than any spacecraft and endured longer than any mountain. It has witnessed the birth of stars and the rise of life, and tonight it carries you gently toward rest. Thank you for spending this time here at Sleepy Discovery. If this peaceful journey helped you relax, you might consider liking this video or subscribing to our channel. It helps others find their way here too, one sleepy soul at a time. But for now, let everything else drift away. Let your breathing settle into its natural rhythm. Let the quiet sound of water in your mind carry you like a gentle current, flowing slowly toward peaceful sleep. The world will still be here in the morning. The water will continue its endless cycle, but you have done everything you need to do today. Now, there is only rest. Sleep well, rest well, and may your dreams be peaceful. Good night.